So the next step is to find the overlap between overlapped intervals, into files. File 1 will be the file, the GFF file that we have for the annotation, which tells us where genes are. And file 2, and we will see how to modify this GFF file in order to have the properties that we want. And file 2 will be the peaks from max 2. Okay, the general idea is the following. If the first file defines an interval here with the black lines, with a specific start and a specific end, and file 2 defines another interval here in blue, and there is an overlap between these two, this area here, then we have an overlap between the two intervals. Now, the idea is the following here. The GFF file defines the beginning and the end of each gene. And the peaks file defines the beginning and the end of each peak. So we have genes in the GFF file and peaks in the peak file. Now we don't really care about an overlap between a peak and a gene, so these two regions here, and the reason is that the peak might be in the promoter region of a gene. So what we need to do is to extend or to modify the area defined by a gene in order to define another region around the gene which is a promoter region. So for example, if the gene starts at the position 10,000 and it is located on the plus strand, and the gene ends at the position 15,000, so this region is about 5,000 base pairs, then we may decide that an interesting region for us is a region that is around the transcription start site here, which is extended 5,000 base pairs on the left up to here, and 3,000 base pairs on the right inside the gene body. And this region, the 8,000, the total region of 8,000 base pairs, is the interesting region for us. So if there is an overlap between the peak and this region now, then we could say that there is an overlap between the peak and the gene. Okay. So in the plus strand, the situation is that we will do the following thing. We have the start and the end of the gene. And in order to define this interesting region here, what we will do is that we will go to the start minus 5,000. So this 5,000 is an arbitrary number. It's just that we will say that the promoter region is 5,000 base pairs upstream of the gene. Starts at 5,000 base pairs upstream for the gene. It extends up to the TSS, but then we say, okay, let's take also some thousand base pairs on the right of the TSS, downstream of the TSS, because also transcription factor might bind within the gene body. So we will modify the start to be start minus 5,000, and we will modify the end being start plus 3000. So this total region will be 5000 plus 3000, 8000 base pairs in total. Now this is correct for the plus strand. For the minus strand, we have another situation. We have again the start and the end of the gene, and these coordinates, for example, let's say that this is 100 and 500, but these coordinates now are defined based on the plus strand. So the 500, even though it's bigger than the 100, it's actually the beginning of the transcription, because now the transcription has this direction. So the transcription start site is actually here, and therefore the interesting region for us is 500 plus something. Okay. So 500 plus something, in order to get this interesting region now, we must say that the start will be the previous end minus something, minus 3000, let's say, and the end, the new end, so let's say here new start and new end, will be again the end plus 5000. So the new end will be here, but the new start will be somewhere here. So this will be 5000 and this will be 3000. Okay. Now we will see in the code a little bit later that we must be careful, because this start minus 5000 might be a negative number. For example, if the start is 4000, then 4000 minus 5000 will be minus 1000, which is a negative number and it's not good. And also this number might be negative. So if the end, for example, as it is here, is 500, 500 minus 3000 will be minus 2500, which is not good again. We'll see how to modify that. Okay, and with this way we can define two intervals. This is the first interval, or in the plus strand, or in the negative strand, this will be another interval. And now if we have an overlap, things will be fine. Okay, let's see how to do that in Galaxy, because this process is not so simple. So the information for every gene is actually given in the GFF file. So let's have a look on the GFF file. I think I have opened it here, yeah. And the GFF file has the following format. It's the chromosome name in the beginning. Then there are some columns that are not very interesting for us, or for example the source. The second column says here that this annotation file has been completed, has been done with a program called Maker. And then the third column is interesting because it informs us that this region is a gene. Then the fourth column is interesting one because it's the start of this feature, of the gene feature. Then we have the end. Then we have some score value. It's supposed to be a score value here, but quite often we have no information, so you just see a dot. Then you see the strand, which is the minus strand here. So this gene is located on the minus strand. Then we have some other information frame, and then we have the group information, which is all this information here. And this for us is interesting because there is a gene name here. And it's a bit problematic that the gene name is within all this mess. So we must find a way to extract the gene name from here, and I will show how to do that. And we need the gene name because later on we're going to find how many common genes we have between the MACs, the peaks, and the RNA-seq. The RNA-seq will report the gene names, but somehow we must get the gene names for each gene here as well. And to achieve that, I used a language, programming language that is called awk, and awk is AWK is written, and awk can run also in Galaxy. So let's see that. We will do that in steps. So I will show something that I did in the beginning and resulted in an error, but I think it will be good to see that also yourself. Okay. So perhaps I should start from here. Let me check if this is a correct file. Yeah, so this was a first simple try. I just tried in the beginning something, but yeah, I think I could show you what I did here, and you will also understand why this is not enough. So you remember how the GFF file looks like. It looks like that. So in the beginning I just need to extract the lines that as a third column, in the third column, contain the word gene. So let's see what I did. So probably I should put a 3 here. I don't know why I put a 4th. Let's run it again. Or maybe, yeah, let's go here maybe. No, this is a bit complicated yet. Yeah, no, I will go to another one. I will go immediately to a difficult file because the input that I need to use this input here. Okay, so I say the following thing. Sorry for the previous mess. I say the following thing. I used awk, and awk can be a bit complicated, but we will go through these lines of code and you will understand what it's doing. So keep in mind that the file has this structure here. So the first column, column number 1, is the chromosome name. Column number 2 we don't need it. Column number 3 is a feature name, so it's a gene. Column 4 and column 5 is the start and the end respectively. The other important column for us is column 7, which is a score, which is a strand, and then so this 7, 8 and 9 is all this information, and from this information we need to extract the gene name. So let's see how to do that within a single piece of code. So I put this curly bracket in the beginning. I will just make this a bit larger so you will be able to see that better. The input is this file that I just showed to you. So I say the following. I start with a curly bracket because this is the syntax of awk, and then I say if column number 3 is a gene, so let's go back here, column number 3 is a gene. So for example, this line, in this line the column number 3 is a gene, and in this line the column number 3 is a gene. But this line in column number 3 there is no the word gene, so I will not do anything on this line. But since on this line there is the word gene, then I say to the program, okay, do something on this line, and what this is the following. So if in column 3 there is the word gene, then do the following. Again check if there is a match on the 9th column with this pattern. So let me explain what this pattern is. This pattern says that on this word here, the word that is in column 9, so the word in column 9 is all this thing. It's all this thing here. All this long thing is one word, is a single column, is the column number 9. Okay. So I say the following. If this column 9 contains something that it is ID equal, and after that there might be the following things: either small letters from A to Z, so A, B, C, D, F, G, but not capital, small ones, or letters from A to Z again, so all letters but capital. So remember that A is the first letter of the English alphabet and Z is the last letter of the English alphabet. So any small letter or any capital letter and any digit. In whatever order, the order does not matter. So for example, it might be that I have so I have any small letter, any capital letter and any digit, and then I have this plus means here at least one time. So for example, let me write here. This word here is okay because I have a capital letter, so this is a letter between A and Z. I have another capital letter, this is another letter between A and Z, and these are 3 digits that each one is between 0 and 9. So then I fulfill this requirement that I have here. Okay, let's see now what I managed to catch with that. You see this ID equals something. So what I observe here is that I have this ID equal, and then I have either capital or small letters or numbers. Many times. I don't know how many times, but there are many times. And then there is this semicolon. Okay, so I say I need to have ID equal, then any sequence of small capital letters and number more than one time, this is the plus, and then have a semicolon. Okay, I observe that this pattern actually is exactly this pattern here, or this pattern here. Sorry, this pattern is not correct because there is a dot. So it's this pattern here, or it will be this pattern here, for example. Now I observe the following. that on genes this pattern is okay, and then this dot one here, which does not fit my pattern, is an mRNA, so anyway I don't care. And then on this gene is okay, the pattern is fine. Then if I continue, go to another gene, for example this one, again the pattern is okay. So I have ID equal capital and small letters, numbers up to the semicolon here. Alright, so it seems good. So I see the following. So let's start from the beginning. If the third column is the word gene, then if on the ninth column there is a match for this pattern, ID equal small capital letters, digits more than one time, then do the following. Then define a name, a variable called name. So this is a name that I put here. I just call it name, and this variable, it's a substring on the column 9. So remember that again, column 9 is all this thing here. So the first letter of the column 9 is number 1, and the pattern that I have might extend. It starts from column 1, and it starts from position 1 of the ninth column and ends on this position, which is, let's say, position 26, just as an example. So this is the I is in position 1 of the ninth column, and 3 here is on position 26 of the ninth column. This beginning and this end here is defined. So sorry, let's say that the end is the semicolon. So the position, the letter I, and the position of the semicolon is defined by this pattern here. So my pattern starts from I and ends on the semicolon. So awk, this language awk, is able to find the starting position and the ending position of the pattern on ninth column of the file. So with rstart, it stores the position of this I, which is number 1, as we said. And rlength is the length of the whole pattern, which is, let's say, 26 base pairs, just as an example. So rlength is the length, not the position of the end, but it's the length. Okay. Which means that the whole pattern starts at the position rstart and has length rlength. So the whole pattern will be this part of the ninth column with the semicolon. This one. In order to get only the gene name part, which is this p-axis blah 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 up to the 3, I must do the following. I should not start at position rstart. I should not start at position rstart, which is the position 1, but I should start the position rstart plus 1 plus 2 plus 3, because this P is 3 positions on the right of I. Okay, but if I will start at position 3, then 3 plus R length will go up to here, up to this position where my cursor is. Because if the whole length is 26, let's say, if I will start from 4 plus 26, it will be 30, and 30 is here. So in order to get back to this 3 here, I must subtract from the R length 4 positions to go up to here. And therefore, with this way, I will get only this part of the 9th column. So what I did here is that I say that the substring is a substring of column 9, but it should start at R start plus 3 and it should end at R length minus 4. Okay, with this way I have taken the part of column 9 that contains the name of the gene. And I have two more complications. Remember that column number 7 is the column that contains the strand information. So I say that if in column 7 I have the plus, then my start here should be the start from the file, so it should be column number 4 minus 5000 if it is on the plus strand. So a plus strand is here. If it's on the plus strand, so here should be this number minus 5000. Column number 4 minus 5000, and the end should be column number 4 plus 3000. Column number 4, this column plus 3000, in order to define this purple region here. Okay. On the other hand, if column number 7 is a minus, so I'm on the minus strand, then the end should be the column number 5 plus 5000, so if I'm on the minus strand, like here, then the end will be this value plus 5000, so it will be this position here, which is the end of the gene plus 5000, and this position, which will be my start actually, will be this position minus 3000, so it will be the end minus 3000. The end, which is column 5 minus 3000. So this is my new start in the case of the minus strand. This is my new end in the case of the minus strand. This is my new start in the case of the plus strand, and this is my new end in the case of the plus strand. And then, if you do all that, just print out the chromosome name, which is in column 1, the start, the new end, the name of the gene, number 6 that contains nothing, the column number 6, which contains just this dot here, and the column number 7, which is the plus or the minus strand. Now this code actually produced a mistake, and when I ran this code, it reported an error. So let's see the error. The error is here. It tells me that there is an invalid record on this file, because start position became negative, and I got this negative value just because here I subtract values. So it might be that column number 4 was less than 5,000, so less than 5 something that is less than 5,000 minus 5,000 will be a negative number. And therefore I made the code a little bit more complicated here. So I modified a little bit and I said the following. Okay, I do exactly the same as I did before. I do all the subtractions, the additions and the subtractions here, the same here, and then I said something simple. Okay, the only problematic variable that I define is the new start variable. And I say if the new start variable is negative, then just make it to be 1. Simple as that. And then I print out column number 1, which is a chromosome name, start, and the name of the gene, the 6th column which was just this dot, and the 7th column which is the strand information, plus or minus. And the result is like that. So chromosome name, start, and gene name here, let's make it a bit smaller. Gene name here, this dot column, and minus or plus strand. And remember that this information here refers only to the genes. There is no exon, there is no mRNA, nothing. Okay, and since I have this now, I can intersect these intervals with peaks information from max2. So for this I use another tool which is called, there are several intersect tools first of all. The one that I use is the BIOL315 intersect intervals. It's this one. Be careful because there is also BIOL315 multiple intersect, BIOL315 window bed. This BIOL315 window bed might be appropriate as well, but what I use is this BIOL315 intersect intervals. And let's see how we apply that. So I click here, and I click here. Okay, let's see. So the camera is not working, but doesn't matter really. Okay, so so I have clicked on this tool and so in file as a file A, what I use is the text reformatting on data 2, which is exactly the file that I was showing to you before. Is this file that defines the promoter regions and the region that I am interested in. So this is file number 1. And file number 2 is the max call peak, the narrow peaks. Then it asks me if I want to use a stranded information. I say I don't want to use strand information, and the reason is that in this max file I don't have the strand information. therefore I need to put that please find overlaps on either strand. Now here the original is like that. I have a bunch of options what to report. So what should be written in the output file? Okay, so if there is an overlap, then I may choose to report the columns from file number A, from file A, so from this file. Remember that this is the file that contains the GIR information. So if there is an overlap in a line between this file and this file, then I can report this information from this file. Now let's try to understand this a bit better. So if, for example, there is a peak that overlaps with, let me open it again here. Now if there is a peak overlapping with this interval here, then Galaxy or this tool allows me to report the information from this file or the information from the other file, from the peak file. But since the gene name is here, I choose to report the information from this file. Okay, so here I can choose write the original entry in A for each overlap, and I remove everything else. The other options, I don't really need them. Here is something that you might want to change. Required overlap, so how much should be the overlap in order to consider that actually there is an overlap, and here the minimum one is 1 base pair, and I just put 1 base pair here. Okay, and I just click on execute. Okay, it finished. So let's see the results. So I have these few, not so many actually overlaps. So I have an overlap on this chromosome, on this interval, and the gene name that I had defined is this one. So let's see how many they are. If I want to see how many they are, I need to download it. Just click here and I save it. And I go here. So this is this file. It's 133 genes. So there is an overlap for 133 genes only in this case. Okay, I hope it was clear. Probably and obviously the most difficult part was the awk command, but I think if you just use the information that I provide to you here, you will be able to get what you need.